Hello everyone. In this video, we will continue to discuss further topics in 9.3 interference. In particular, we will discuss diffraction grating interference patterns and solving problems involving the diffraction grating equation. So, as you increase the number of slits, you get a number of patterns, as discussed in the multiple slit interference section. Those patterns, taken to their logical extreme, result in patterns we recognize as belonging to diffraction gratings. And all a diffraction grating is a tool with many slits. Okay, so there's no sharp line between multiple slits and a diffraction grating, but as you increase the number of slits, you start to get patterns that look more and more similar. And those patterns have very sharp peaks, okay? Very sharp, distinctive peaks, and no discernible secondary maxima. So that would be that sort of dividing line between a multiple slit pattern and a diffraction grating pattern is that there are no discernible secondary maxima. And you usually characterize a diffraction grating in terms of sort of the number of lines per millimeter, because you're going to illuminate the diffraction grating with a laser of a fixed width. And so you usually build them so that the laser will sort of cover a certain number of lines. So instead of characterizing it as a total number of lines, they're characterized as the number of lines per millimeter. And we're talking somewhere in the hundreds of lines per millimeter for a typical diffraction grating. And what happens for a typical diffraction grating is that all these effects that we were discussing, okay, add up. So you simply add up the sort of double slit and triple slit and quadruple slit, etc. effect for hundreds of slits at a particular angle. And what you will see is that you will see these maxima here at those predictable angles. So that central maximum right in the middle where light comes from each slit in the diffraction grating equally. There's no path difference between them. And then integer path differences for the first order, so a single wavelength path difference, 2 wavelengths path difference for the second order line, and so on and so forth. If you have a non-negligible slit width, if that single slit pattern is still visible, you will still see it modulating the diffraction grating. But in most cases with a diffraction grating, we will assume a negligible slit width. The slits themselves are so narrow so as to obscure any kind of single slit effect, which you can sort of barely see in this graph here. So for a diffraction grating with slit separation d, so the distance between the slits is little d, just as in our double slit equation, we can actually derive a formula for the angle we expect those fringes to occur at. And we can do so by sort of considering the light coming from each particular slit as coming from a single point source. As in the double slit case, you can imagine light coming from these top 2 slits as being in the double slit case. We can define the path difference here and its relationship to that distance d. And that's indicated with a small delta here. And then the only thing to observe is that as you, if you have an even slit spacing, then if you go not just 1 little d away, but 2 little d away, you will see that the path difference then becomes exactly 2 delta, assuming that these lines are parallel, assuming that the screen is far enough away that we can assume that the rays are parallel as they leave the slits. And you can see this by appealing to geometry. These are similar triangles, so they have the same angle here, here, and so on and so forth, and therefore this small side grows by the same factor as the hypotenuse. As a result, you get constructive interference in particular when m delta, okay, so m being sort of the order of this, the number of slits, divided by md, that is the distance between the slits, is exactly equal to sine theta. And therefore you get bright fringes where n lambda, so that's the order of the diffraction, is therefore equal to d sine theta, because the path difference is equal to little d times sine theta. So again, this m over here has to do with which slit you're talking about. This first gap, this second one, this third one, this fourth one, so on and so forth. And that is a different integer than this one right here, which has to do with simply adding up, with the order of the fringes. So are we talking about a path difference of 1 wavelength, 2, 3, 4, etc.? As a result, the equation associated with the diffraction grating is written like so, where you get the order of the diffraction times the wavelength is equal to d sine theta. Okay, this is a pretty similar equation to the others, so make sure to keep it straight. And one more complexity. Unfortunately, diffraction gratings tend to be specified not in terms of their slit spacing, little d, but instead in terms of the number of lines per millimeter. So this is just the typical thing you'll see on a diffraction grating, but it's very easy to convert. If you take the number of lines per millimeter, invert it, and convert that per millimeter to per meter, then d is equal to 1 over n times 1,000, and so you can use the diffraction grating equation, and lambda equals d sine theta, by using this simple conversion for your diffraction grating.